welcome back to another session of why we shouldn't chase formulas. And in today's topic, I am going to discuss Newton laws of motion. All right, yeah. So if you look at a Newton laws of problem, just like this, you immediately tend to go to write, all the equations, all the mg value, mg tension, and you tend to write the equations and then solve the acceleration and the tension all the time. But I'm not saying there are no formulas involved in this thing. I'm actually asking you to look at the problem in a practical manner, try to feel it more instead of writing the equations. We are actually doing the same thing that we do through equations, but if only you practically see the situation, what is happening there, you would easily try to, you can easily try to solve the problem much quicker. That's what I'm trying to say. All right. So let's start with this problem. All right. When you have a situation like this, you can try to feel this thing that this block right here is providing all the force for the system to accelerate, and this block right here is just being a lazy ass. Do you agree? It's not actually providing any gravity, it is just being lazy and being dragged. That is how I want you to see it. So this is providing the force, this block is providing the force, and it is being dragged. So the whole system is purely dependent on this mass here. So that is the only force that is being dragged. Let us take a mass as m1 and this as m2. So the whole system is actually depending on m1g, but who is accelerating? Both are accelerating. So the net acceleration of the system, like net acceleration of any of those bodies, must be m1g, the F net by total mass who is being driven. So the simple way I would put it is, like, when you try to find a problem, when you try to find the acceleration in a problem like this, the first thing that you should is look at all the force that is driving the system. Force driving by the mass driven. This is how I look at the system every time. I'm not, this is a formula, but I want you to feel it this way. Okay, look at this problem. If only I have a problem like this. Here both the masses are clearly trying to drive the system, and both the masses are being driven, but one mass is trying to drive it one way and the other mass is actually trying to drive it in the other way. So I would actually take this m1 and this m2, like m1g in this direction, m2g in this direction, and both are being driven. Let us say the system is accelerating like this. So I would put m1g minus m2g. That is the net force is responsible for the system which is being driving by m1 plus m2. Yeah, you might have seen this formula already, but you're feeling it practically. Let us look at this situation in a simulator, the same website, ophysics.com. I'm going to put down the angle to 0. And if only you look at the forces, you can clearly feel, I'm sorry about that. I'm bringing on the friction also. You can clearly feel this is the only thing that is actually driving the system, and this is being a lazy ass, right? So I want you to practically feel it and look at it. I'll just take out and run it. M1g is the only responsible force who's driving it, and M2g is being completely a lazy ass. So when you try to write the system, but try to write the acceleration of the system must be M1g by M1 plus M2. Look at, if only the system is like this. Here both the masses are being responsible, m1g and m2g. m1g is trying to run the system in one direction, and m2g is trying to run the system in the other direction. So if only I run it, you can clearly see both the masses are clearly trying to offer. m2g is trying to offer in this direction, m1g is trying to offer in the opposite direction, right? So I would like to write m2g minus m1g, but both the masses are accelerating. So it is as if m2 plus m1. It is as if the system is dependent on both the masses, both the weights, and both are accelerating. In the previous situation, the whole system is clearly being dependent on one mass, one weight. Both the masses are being accelerated. You get the point? Now, if only you apply this idea to all the problems. Until now, yeah, you might have seen this thing, you might have seen this expression in a lot of situations, but you can apply this idea to all the problems in physics, almost. Let us see. In this situation, let us take this as 2 kg, let us take this as 6 kg, and let us take this as 4 kg. Here, obviously, both 6g and 2g, both are trying to accelerate the system, 6g and 2g. and 4g is the one who's being a lazy ass. So I would directly write the acceleration of the system as 6g minus 2g by who is being accelerating? Everyone is accelerating, right? So 6 plus 4 plus 2. If you check the acceleration using all the equations, you would definitely get the same answer. Okay, you can in fact use the same idea on an inclined surface also. Except in this inclined surface, you need to be careful saying, yes, both the weights are responsible, but let us call this as M1 and let us call this as M2. But here M1g is entirely responsible, but M2g is not entirely responsible. It is just M2g sine theta that is responsible. So when I try to write the acceleration of the system, both are accelerating obviously. So the net force who is trying to drive the system, the entire net force, M1g minus M2g sine theta. That is the net force who is trying to drive the system, and who is being driven? The entire masses, all the masses, M1 plus M2. You can in fact extend this idea. I hope it is clear. You can in fact extend this idea all the way when you have a 3-block system. This might look a bit difficult, but try to follow me. M1, M2, M3, and the angle is theta. If you are smart enough, you must already know that M1g is trying to drive the system in this manner, in this direction. M2g is trying to drive the system in this direction, and M3 is not completely being a lazy ass here. M3g sine theta, a bit of it is actually trying to drive the system. So when you write the net force who's driving the system, let us say the whole system is accelerating in this direction. So M1g plus M3g sine theta minus M2g by the entire mass who's being driven, M1 plus M2 plus M3. If you do this, you directly write the acceleration of the system. That is how it is. That is how simple it is. All right. Now, let me take you to the next idea. You can in fact tell the tension in the problem also. Yeah, a big surprise. Not just the acceleration, you can in fact directly feel the tension in the system. But before I tell you how the tension works, I think you need to subscribe to the channel, otherwise you won't be able to watch it. I'm just kidding, guys. It's fine. Okay, let's get to the point. So let me take you to the original problem itself. All right. M1g, M2g. So how do I find the tension here? So let's look at this tension. Now, what is this tension responsible for? That's what you need to do. You already found the acceleration in the previous situation, in the previous idea, using the previous idea, you already found the acceleration. So look at this acceleration. This tension is purely responsible for M2 into A. This is an equation that we already know, but if you only practically feel it, there's a huge advantage. You can directly write the acceleration, you can directly write the tension also without even putting your pen on the paper. All right. So this tension is responsible only to M2A. So since you already found the acceleration, put the acceleration in there, and you directly give the answer. Like, look at this situation. I'm going to give you an example. 3g, 1g, 1 kg. So obviously, if you are quick enough, the acceleration must be 3g is the only one who's responsible to drive the system. Who is being driven? All the masses are being driven. So that is the acceleration, 3g by 4. That's all. Now, once the acceleration is clear, this tension is only responsible to drive this mass with an acceleration. So tension equals to mass into acceleration, this mass into acceleration, that mass 1 into 3g by 4. That is the tension in the system. That's all. You don't even have to put, you are actually putting this acceleration back in the equations, but you're just looking at what is this tension responsible for, just this mass to accelerate. That's all. Now look at another problem. In this situation, 4 kg, 1 kg. Yeah, what is the acceleration, guys? A quick answer. Make it your mind. Acceleration, 4g and 1g, both are responsible. So the net will be 3g. Who is being accelerating? All the masses, 4 and 1. So 5. That is the acceleration. If you got it quick enough, that is great. All right. Now look at the tension in this situation. Yeah, you can use both the masses, but I'm using the smaller mass. It is easier. Now this tension is not just accelerating the body. Now try to feel this point. This tension is not just accelerating the body, it is also opposing the weight of the system, weight of this mass. So the weight of this mass is The weight of this mass is already 1g, plus it is also giving the 1a. I want you to practically feel this thing, 1g and 1a, both the idea, both the weight and it is providing some acceleration. So the minute you have it, g plus 1 into a, 3g by 5, that is the tension in the system. Yeah. What you're doing is you're actually putting it in the equation, but when you practically feel that what is this tension responsible for? This tension is responsible to balance the weight of the body and also accelerating the body. So if you look at that, if you look at the problem in that angle, you will definitely be able to answer any of the kind of questions. And look at this question that I'm developing here. Yeah, you can immediately give the acceleration of the system, but once you have the acceleration, like let us say I've given you masses 4, what happened here? Let's say you have a problem like this now, 4 kg, 5 kg and 1 kg. You can immediately give the acceleration saying if you are quick enough, 5g, 1g. So responsible is 4g and all the masses are being accelerated. So 5 plus 4 plus 1. So that is the acceleration of the system. So let us look at the tension here. This tension is responsible not just to balance the weight, 1g, it is also providing 1a also. So if you add these two values, put this acceleration here, you also find the tension. If you want to find the tension here, this tension, I want you to look at this problem in different angle. This tension is not able to balance the weight because the body is accelerating downwards here. The body is accelerating downwards here. So this tension is fighting against the weight, but it is failing. So this tension, this T2 value is less than 5g by value of 5a. You see the point, right? You're looking at the point. The 5g is more here. The tension is losing its fight against the weight. So 5g minus that 5a value. So here 5g is fighting against T2. Let's look at that way. 5g minus that acceleration providing content is tension here. Okay. So now what I'm trying to say is try to solve the problem that you always do in the same manner and try to solve these problems in this manner and try to correlate them. If you do enough practice, you will be able to give the answer right away looking at the problem. You won't even take enough time. Okay. That since I have done enough practice on these type of questions, I can in fact give an answer even by looking at a problem like this. This involves constraint relations. Let us take 1 kg and 3 kg, and I can directly say the answer, the acceleration of this body would be g by 7. Yeah, I would directly answer that. Since I've done enough practice on these kind of problems in the past few years. So if only you can kind of develop this kind of intuitive idea towards these problems, solving of all these problems would be really quick and it would definitely help you in the problems of mains. Question time. So I thought I'd give you a question at the end of every video I'll be making from now onwards. So look at this question. You have these blocks accelerating one up and one down, but in constraint relations, we were always told that each and every point on these strings must be accelerating with the same magnitude. Even these points on the other side of the string also must be accelerating with the same magnitude. That's what we were told, right, in constraint relations. But my question is not about these points. My question is about the points on these things. Now, do they also have the same acceleration? That is the question, guys. All the points on the pulley, do they have the same amount of acceleration or not? If you say yes, now the question is, if they are going in a circular motion, do they really have a centripetal acceleration? That is the question. If the acceleration of those points is also a, along with that, do they have a centripetal acceleration? Now, if the acceleration is not same for all the points, in constraint relations, we were clearly told that if the acceleration of all the points on a string must be same, otherwise the string would break. Now, what exactly is happening here? Now, try to let me know about that in the comments, and also let me know about which topic do you want me to discuss next. Alright guys, so thanks so much and bye-bye.